There we go. Now we're recording. All right. Well, I thought tonight I would look at the exam 4 practice questions, which are available on Canvas. We'll start with this one. These are ones I've culled from past exams that relate to the current exam. So over here, we've got a Diels-Alder reaction, and so we need to find the product. It becomes a little easier to see if we rotate the dienophile by 90 degrees, like this, and then bring the two molecules together. And then, just as we discussed in class, the electrons move 3 electron pairs all at the same time. And again, if you wish to draw dotted lines, you may. It's optional. You can if you like. You don't have to. And again, the arrows can go either clockwise or counterclockwise. It doesn't matter. And we should get a cyclohexene derivative out of this. So the methyl group stays in the same place. Of course, we don't put a wedge or dashed bond on the methyl group because it's on an sp2 hybridized carbon. So that part of the molecule is flat. And then we would have another double bond over here. The triple bond in the alkyne became a double bond when it lost 2 of the pi electrons. And on those 2 carbons, we will simply have methyl ester groups. Just like this. And that would be the product that I would expect. The next question is also about a Diels-Alder reaction. And the big hint we have about this is that we've got this conjugated diene that somehow turned into a cyclohexene derivative. There's the double bond in the cyclohexene. So what we need to do in order to figure out what the other starting material was is run the Diels-Alder reaction in reverse. So this sigma bond will move over there and make a pi bond. This pi bond moves over here, and this sigma bond moves over there. Again, in any Diels-Alder reaction, without exception, you always form 2 new sigma bonds and 1 new pi bond. And so if we run that backward, essentially we're talking about what the starting materials for the Diels-Alder reaction were. And then you just write down what you get, and you get an extremely bizarre species. There's your diene, and you can see that's the same molecule as the diene that we were given. The other species is something truly bizarre, which is mentioned in chapter 16, though we never talked about it specifically. It's benzene. And benzene is a known intermediate that you can make, obviously exceedingly strained and reactive. But it is also a truly wonderful Diels-Alder dienophile because the amount of strain in that ring is just tremendous. And so by undergoing the Diels-Alder reaction and making this product, you get rid of all that strain. So in order to figure out what the other material is, this is what you would put in the box, is the benzene. The diene is already there. So, so that would be the answer to that question. Let me turn on the chat. I don't know exactly where I'll put it, but maybe over here. So the next two, I think we need to deal with together. Because in both of them, we're starting with a conjugated diene and making a dibromide. So it looks to me like in both cases, we've reacted the diene with Br2. And in one of the cases, we formed the 1,2 product. We know that because the two bromines are on adjacent carbons. And in the other case, we formed the 1,4 product. And whether you start numbering from top to bottom or bottom to top doesn't matter. Either way, you come to the same conclusion that the carbons that the two bromines are on are in a 1,4 relationship to each other. So in both cases, we're treating the conjugated diene with bromine, but in one case, we get the 1,2 product. And so in that case, we would be treating it with bromine at a low temperature. And in the other case, we'd be treating it with bromine at a high temperature. And I don't think it's necessary to mention specific temperatures. I don't remember exactly how the grading went on this exam, but if anyone had put BR2 and 0 degrees or -20, that would have been completely fine. And for this one, if they'd put BR2 and 40 degrees or 60 degrees or something like that, I'm sure we accepted it. But it's not necessary. Low temp and high temp are good enough. So this whole page was on chapter 14 stuff, or at least all these questions were, on the Diels-Alder reaction and on electrophilic addition to conjugated dienes. And that's pretty much it for that. I'm being very quick about erasing things because they're permanently on, they're going to be permanently on YouTube. Again, I hope as early as tonight. We'll see how it goes. So on the next page, we looked at a question just like this in class today. It says D-talose is an aldohexose like dihexose, except it differs in configuration from glucose at carbons 2 and 4. Draw talose in its open chain form, its chair form, and its Haworth projection. This says the way we did on YouTube, this clearly comes from one of the COVID semesters. So I would say instead the way we did in class, since we're back to having class as normal. For the two cyclic forms, draw the beta anomer. All right, so I am going to, just to save some time, pull out a Fisher projection. And again, it's totally fine if you want to abbreviate the aldehyde group as CHO. My experience is that the majority of students today don't like that. And so if you want to draw out the aldehyde group as normal, that's totally fine. And as I said, I chose to put the oxygen on the left and the hydrogen on the right. Obviously, if you put the hydrogen on the left and the oxygen on the right, it's just fine. We won't even notice. It's clearly the same structure. And so now all we need to do is put all the OH groups in the right place. And we can understand what talose is by comparison to glucose. It differs from glucose at carbons 2 and 4. So let's not forget what glucose is. The OH groups go right, left, right, right. And H is in the other positions. So this is D-glucose. And in order to get D-talose, we'll simply change the configuration at carbons 2 and 4, just like the problem says. So let's remind ourselves of the numbering. There we are. And obviously, the problem doesn't say to number the carbons or to draw D-glucose. Also, I'm just doing it so that everyone has a clear visual aid. And so we're going to need to change the configuration at carbons 2 and 4. So we will change it so that the OH group points to the left on carbon 2 rather. And also to the left on carbon 4. And so this would be D-talose. So as you see, it differs from glucose at carbons 2 and 4. This OH, of course, we must never touch, as long as we're dealing constantly, as we will be, with D sugars, because the D sugars have to have that OH on the penultimate carbon pointing to the right. If that changed, we would no longer have a D sugar. We'd have an L sugar. So in order to draw talose in the chair form, and again, I can do that fairly easily. Let me just erase all these. I just want to get, well, I can leave the CH2OH. So there's our chair form with all of the bonds showing the correct bond angles. And so we've learned that in glucose, except for at carbon 1, where the direction the OH points depends on whether we have the alpha anomer or the beta anomer. So there's the numbering of the carbons. It says to draw the beta anomer, so that means the OH in carbon 1 will point up. And if you're having trouble telling that this OH group is up, then you look at the H on the same atom. That H is definitely pointing down. There's no question about that. So the OH must be pointing up. Meanwhile, in glucose, the OHs would be in the equatorial positions on carbons 2, 3, and 4. But we need to change carbons 2 and 4, because that's what the problem says to do. It says talose is like glucose, except it differs in configuration at carbons 2 and 4. So we will leave the OH equatorial in carbon 3, and we will make it axial on carbons 2 and 4. And again, I'm not sure how you guys feel about drawing the CH2OH like that. Drawing the bolded lines is optional. You don't have to do that to get credit. It does kind of look nice, but it's thoroughly optional. But if you just did something like that, it would be completely fine. And again, if you would rather draw the CH2OH just like this, text, I think it's flush left. Then that's, of course, completely fine. Not only will we not take off points, we won't even notice. Again, I'm hoping that the majority of you are confident enough in drawing structures that things like that don't faze you anymore. You're confident that that's the same thing. It must be. There's no way it would not be accepted. It's the same structure, just drawn a different way. Good, so that's the chair form. And as I've said, I never bothered memorizing any Hayworth projections. I just get them based off of the chair form. So in the Haworth projection, we make pretend as though the ring is flat. We again put the oxygen in the upper right. And we attach these bonds with these thoroughly, again, I'll use the word scuffed bond angles. That's nowhere near the actual 109.5-degree bond angles that we know are going to be present on an sp3 hybridized carbon, but by convention, that's how Haworth projections are formed, and we just copy what we see on the chair form. On carbon 1, the OH group is pointing up, and again, if you're ever having trouble telling whether a group is pointing up or down when it's equatorial, look at the axial group. That will clarify that for you. Whatever the axial group is, the equatorial group must be the opposite. If the axial group is pointing up, then the equatorial group is down. If the axial group is pointing down, then the equatorial group is up. So the OH in carbon 1 is pointing up. The OH in carbon 2 is also pointing up. And again, if the problem doesn't say to number the carbons, you don't have to. I'm just doing it to give everyone a clear visual aid. On carbon 3, the OH is again pointing up. On carbon 4, lo and behold, the OH is pointing up. And on carbon 5, the CH2OH must always be pointing up in a D sugar. So here's carbon 3, here's carbon 4, here's carbon 5, and the CH2 is carbon 6. So something like that was what I was looking for. It's just a coincidence that all of the groups happen to be pointing up. I don't think I planned that. So that's what I was looking for in answer to the first part of the problem. And I'm pretty confident in myself, but just let me make sure I'm not lying to you. Yep, everything's pointing up. Yep, looks the same. Good, so I am going to keep that D Talos there just for a moment. I might not be able to do that. Let's see. Now draw L-Talos and L-glucose in their open chain forms. So there's D-Talos. L-Talos, and this is very important, would have all 4 chiral carbons switch their configuration. It's the enantiomer of D-Talos. A very common mistake that I see on exams is people will just switch the OH at carbon 5. That is not the enantiomer. That's a diastereomer. So whenever you're going between the D and L forms for any given sugar, you need to change the configuration at all of the chiral carbons. That's by definition of the word enantiomer. In an enantiomer, to get the enantiomer of something, we change the configuration at all of the chiral carbons. If we change only one of them or only some of them, you don't get the enantiomer. You get a diastereomer. So L-Talos is the enantiomer of D-Talos. And then L-glucose instead of being right, left, right, right, will be left, right, left, left. So left, right, left, left. And then it says, draw the only 3-carbon sugar we discussed in class that is not chiral. And there's only one candidate for that. It's 1,3-dihydroxyacetone. It doesn't ask for the name, so we don't need to put it. If the question asked for the name, we'd put the name. So that's 1,3-dihydroxyacetone. We'll run into that guy again very soon in chapter 29. It shows up in glycolysis, I believe. Good, so much for that. Now we just have the third part of the question to worry about. Draw the disaccharide D-glucose beta-1,6-glucose, D-glucose. So we're going to start with D-glucose. Notice again very carefully the shape of the chair that we need to use. That's the correct chair for drawing D sugars, not this one. That shape is wrong, and I covered that in the class notes. You need to always use this shape of the chair in order to draw D sugars. So there's our glucose. We need the beta anomer in which the oxygen points up. So there's our D-glucose. Again, notice in carbons 2, 3, and 4, the OHs are all equatorial on glucose, as is the CH2OH coming off of carbon 5. Then we need to connect carbon 1. This is carbon 1 of the first glucose. And we need that oxygen to be beta, in other words, pointing up. And then we need to connect that oxygen to carbon 6, which is the CH2OH carbon of the next glucose. So again, I can do things that you can't easily do with a pencil. But I'm just going to take another glucose and move it over so that I can connect that CH2 to the OH like this. And so this is carbon 6 of the other glucose. We've made a beta-1,6 linkage in order to connect the first glucose to the second glucose. It also says at the hemiacetal, draw the alpha anomer. I currently have the beta anomer over there. So to draw the alpha anomer at the hemiacetal carbon, we're going to make that OH point down. And so there's only one hemiacetal carbon. These are terms you need to know in order to understand this material. What is an acetal and what is a hemiacetal? So the hemiacetal carbon is also called the anomeric carbon. It's carbon 1 of the second sugar. And remember, a hemiacetal is defined as a C that has OH and OR attached to it. So that's your hemiacetal carbon. And I believe that's correct. I will check myself just in case. Let's see. Well, my drawing on the answer key is a little prettier, but this is certainly fine. Good. So much for that question. On the next page, we have we used to have OWL instead of active. So this is an active style synthesis in which you need to put in all of the reagents. And so you need to recognize your reactions. Some of these come from organic one. The first one, when we compare the two structures, the starting material and the product, we can see that the secondary alcohol has been oxidized to a ketone. There's a few reagents that can do this. The one you guys learned about was desmartin periodinane in dichloromethane. And then in the next step, we've attached this isopropyl group and we formed a new carbon-carbon bond between the isopropyl group and the carbon that had been a carbonyl carbon. And also, we've gone from a carbon-oxygen double bond to a carbon-oxygen single bond. That can only happen by treatment with a Grignard reagent or an alkyl lithium. So the first step would be treatment with a Grignard reagent. So let me just remind you of what IPR means. IPR is an isopropyl group. So you've got the connection at that second carbon. IPR is an acceptable abbreviation for the isopropyl group. You may use it if you like. It's perfectly acceptable. And so we've got isopropyl Grignard. Obviously, if you had MgCl or MgI, it's fine. It doesn't have to be a bromine. And you need some sort of ether solvent. Diethyl ether is fine. THF is fine. And of course, if instead of a Grignard, you wanted to use an alkyl lithium, it's completely fine. The exact same thing would happen. We've been pretty clear about that. Grignard reagents and alkyl lithiums have identical reactivity. And then you also need some kind of aqueous acid workup. We went over the mechanism of the Grignard reaction in chapter 19. So if you've forgotten the mechanism, please review that. It's good review for the final exam. And you do need the aqueous workup because at first you get O-, and so you need to put the proton back on the oxygen. So it needs an aqueous acid workup. In the next step, when you compare the two structures, you're going from C single bond C to C double bond C, and you're losing an H and an OH. In other words, you're dehydrating. We talked about a dehydration reaction just today. There are a lot of dehydrating reagents. The one we used today was acetic anhydride. And if someone put that, I would have accepted it. There are other really good dehydrating agents like phosphorus oxychloride. Thionyl chloride is another good one. In fact, if someone even just put sulfuric acid, that's fine. Concentrated sulfuric acid is a very good dehydrating agent. Let me see if I forgot any. Nope. And of course, at that point, we were still using chromium reagents like PCC and chromium 6 oxide. Those have fallen out of favor. But if you were to put something like that instead of DMP, that's fine. So that would get us the alkene. When you compare that structure to the next one, we've added a Cl and an OH. This is a chlorohydrin. We talked about forming halohydrins in chapter 8. So this is a chlorohydrin. And the reagents for forming a halohydrin are the halogen and water. So yes, I still do expect that you know all of the organic 1 reactions. This is one of them. And then also in organic 1, in chapter 18 especially, but also in chapter 8, we pointed out that you can take a halohydrin and make an epoxide out of it by treating it with a base. And the mechanism is that the base pulls off the proton from the OH group to give you O-, and then the O- attacks the carbon that bears the halogen and does an SN2 reaction and expels the halide. So any base, NaOH and water would have been completely fine. Any strong base is fine. Sodium amide, fine. Sodium methoxide and methanol, fine. Any strong base would be fine. Right, I said NaOH, H2O, or other strong base. So any strong base is fine. So much for that synthesis. In this one, we're starting with an alkyne. And if you compare the structure of the alkyne to the next one, we've gone from an alkyne to a cis-alkene. The reagent for doing that is hydrogen and Lindlar's catalyst. That would have been in chapter 9. That converts an alkyne to a cis-alkene. It reduces an alkyne to a cis-alkene and stops. If you wanted to reduce the alkyne all the way to an alkane, then you just use an excess of hydrogen and palladium or one of those other transition metal catalysts. But if you wanted to stop at the cis-alkene, then you use Lindlar's catalyst. To make a transalkene, you would use either lithium or sodium metal and liquid ammonia. So those are chapter 9 reactions. In the next reaction, if you look at what's changed in the molecule, we've changed the OH to a Cl. In other words, we've converted the carboxylic acid into an acid chloride. And that's a reagent I would expect you to know, thionyl chloride. And usually with this, we add some kind of mild base like pyridine or triethylamine, but even without, it would still work. And that's what I have in the answer key. Next, we go from the acid chloride to an ester. And we talked about that in chapter 21. In order to go from an acid chloride to an ester, you need to do an alcoholysis. And we would, in this case, use ethanol. You could also do it under alkaline conditions and treat this with sodium methoxide and ethanol. Either way, you will get the ethyl ester. So that's a chapter 21 reaction. This is all good review for the final exam as well. And then the change from here to here, we seem to have done a cyclization. And we talked about the types of dienes that will undergo a Diels-Alder reaction to make a bicyclic compound like this. And we notice in particular that the hexyl group and the ethyl ester are cis to each other. They're both pointing down. They're also cis to each other in this compound, which is going to turn out to be our dienophile. And it would be a good dienophile. It has an electron poor atom attached to the alkene portion. So the part that's missing is cyclopentadiene. And cyclopentadiene will do a Diels-Alder reaction with that dienophile to give that Diels-Alder adduct. Next one looks like we're making an amino acid. In fact, this is nothing other than proline. And this synthesis would work to make proline. You'd get a mixture of D and L proline, but you would make proline. In the first step, we're changing a CH2 to a CHBr. We've replaced a hydrogen next to a carboxylic acid with a bromine. That's a reaction we talked about in chapter 20. And the reagents are bromine and phosphorus tribromide, followed by an aqueous workup. You need the aqueous workup because phosphorus tribromide will also convert the carboxylic acid to an acid bromide. And so you need to hydrolyze that to go back to the carboxylic acid. Once you form that, you can very easily put a nitrogen in between doing two SN2 reactions just by treating it with ammonia. And then in order to get the form of the amino acid that you see there, you would need to bring it to pH 7. I don't know how picky I was on that part, but technically you would need to bring it to pH 7. And I think I have that on the answer key also. I don't, so I guess I didn't really care either way. But technically you would need to bring it to pH 7. But for now, I will say that didn't have to be there to get credit. Just the excess ammonia. Good, so much for those synthesis problems. After this, we have some problems where you have to fill in the product. I think you guys are used to this by now. The first one ought to be fairly straightforward. We did that reaction in class today. And today wasn't the first time we've seen this. We talked about how if you treat an aldehyde, any aldehyde, doesn't have to be a sugar, with sodium borohydride in aqueous methanol or ethanol, you will get the corresponding primary alcohol. If you start with an aldose, you will get a sugar alcohol or alditol. And so that would be the product that you would get. The next one looks to me like a Michael addition. We're starting with this compound, which has two particularly acidic hydrogens between the two ketone carbonyls. We're going to deprotonate that with sodium ethoxide, which is a good base. And the enolate is then going to add to the beta carbon of the alpha beta unsaturated compound. And then after an acid workup, I anticipate that we would get an adduct of the enolate attacking that beta carbon. So let me just give a visual aid. So the beta carbon's over here, and the alpha carbon's over there. And enolates are one of the nucleophiles that prefer to add to the beta carbon than directly to the carbonyl. You don't have to do the mechanism on these problems. It doesn't say to, but you might need to in order to be able to see the product. So we start by pulling off one of the protons, one of these acidic protons. That gives the enolate. There's the enolate. And the enolate then adds to the beta carbon. Yeah, I really kind of have to draw it like that, but let me see if I can at least make it end in the right spot. So that's not the prettiest arrow in the world, but it will have to do. You attack at that beta carbon, and the next intermediate that we get is also an enolate. So that's the new bond we form. That's going to form a new bond to the carbon that's next to the benzene ring. Kind of have to go like this. And so you get that enolate until you add the dilute aqueous acid. That enolate then gets protonated at carbon. By a hydronium ion. And that's going to be the answer to the question. It would look something like that. I don't believe it will react further, but I'll just make sure. Oh, wait a minute, was that a hydrogen all along? Yes, this is a hydrogen, not a methyl group. There we go, that's better. You can see it was a hydrogen all along. So that's that one. The next one starts out exactly the same way, but we're just treating it with a different dienophile. I'm sorry, a different electrophile. The difference is now the electrophile is benzaldehyde. So you just put that there as the recipient of the electron density. Well, I don't have to draw the H. It's understood. So at first you will get the, at first you will get this alkoxide ion. Again, this aldehyde hydrogen is still there, I just didn't draw it. And then that alkoxide picks up a proton from the solvent, which in this case is ethanol. That will give us the aldol addition product. And then since if you follow the rules that we gave in chapter 23, this one's going to dehydrate because we have this benzene ring right next door. And so once we dehydrate, the new double bond will be conjugated not only to both carbonyls, but also to the benzene ring. So this is one you don't even need to heat. This is going to dehydrate no matter what. You couldn't stop it from dehydrating if you wanted to. So we start by deprotonating. Actually, just to make my life a little easier, I'm going to show the deprotonation on this side, but it doesn't matter. So ethoxide pulls off that proton. You form again the enolate. So there's your enolate. And then, as we discussed, the enolate collapses. You do the second step of the E1CB reaction. We reform the carbonyl, the double bond shifts over one place, and we expel hydroxide as the leaving group, and that's going to be the product. And again, we have that new double bond that's conjugated to both carbonyls and to the benzene ring. So there is no way, in my belief, that you could stop this one from dehydrating. And that's going to be the answer to that question. It's just another aldol reaction. Well, I shouldn't say another aldol reaction. I think that's the only aldol reaction on this page. So that's the product that I would expect. Yep. Now, as for the next one, this one I don't think we even need to write the mechanism. The first step is going to form the very same enolate. And then that enolate will attack 1-bromobutane. Well, why should I be so stingy? I might, since I have it here already, I might as well show the enolate forming. But we formed the very same enolate. Actually, I think I'll make my life easier if I draw 1-bromobutane this way. The enolate will then attack 1-bromobutane at the carbon bearing the leaving group. The leaving group then leaves. This is an SN2 reaction. And the product that I would expect would simply have the butyl group there between the two carbonyls. like that, just as per the answer key. And we could argue whether the base would pull that proton off and you'd then need an acid workup. That's up for debate, I suppose. But either way, whether it needs an acid workup or not, that's going to be the product. Okay. Last but not least. Oh, it's not last. The next question is another aldol condensation reaction. This is going to be a self-condensation. So you'll use two of the same molecule. We're going to start by deprotonating in the only place we can deprotonate, which is alpha to the carbonyl. There's only one set of acidic hydrogens. So that's where we'll deprotonate. Oh, I forgot to draw the arrow. There we go. That's better. So we deprotonate. We'll get the enolate. Which looks like this. That enolate will then add into another molecule of the same. And so we reform the carbonyl. Enolate then attacks. These electrons will remain attached at that carbon and form a new bond between that carbon and the carbonyl carbon. So there's the new bond we formed. I'm going to have trouble fitting these things in. We'll have a tert-butyl group. We'll have a methyl group. And we'll have O minus. So that's the intermediate. That intermediate is going to pick up a proton from the solvent, which in this case is ethanol. It might not always be ethanol, but it is in this case. Whatever the solvent is, could be water, could be methanol, could be ethanol. Probably 99.9% likely it's going to be one of those three. That will give that tertiary alcohol. And then the dehydration will commence. We know it's going to be dehydrated because it says heat. So that's going to initiate the dehydration. The tendency to dehydrate is pretty strong even without the heat, but since it says heat, we can be absolutely certain. So the first step is deprotonating alpha to the carbonyl. That will give an enolate that looks like this. And then the enolate will collapse. We'll do the second step of the E1CB reaction. The double bond will shift over one place, and we'll lose hydroxide as a leaving group. Again, a thing which could never, ever happen in acidic solution. But in alkaline solution, we can rationalize it. And now let me just think what the stereochemistry is going to be. I think these two tert-butyl groups are going to want to be as far apart from one another as possible. So I think those two groups will be trans, or E, if you will. And then the double bond will be over here. I think the other tert-butyl group is going to be over here. And then the methyl group on the other side. And we need the oxygen and the carbonyl. And I believe that's it. Let me make sure I didn't mess something up. Looks good. Yeah, I'm confident that's going to be the major product. That's the more stable double bond with the two bulky tert-butyl groups as far apart from one another as they can get. And then, last but not least, we're going to do something real similar, except it's going to be a Claisen condensation reaction, a Claisen self-condensation, using two of the same molecule. So in the first step, our base, which is in this case ethoxide, will pull off one of the alpha protons. Oh, I forgot my minus charge. There we go, that's better. Ethoxide will pull off one of those acidic alpha protons. If anything, having the benzene ring there makes them slightly more acidic still, because you get a resonance stabilized carbanion. Benzylic carbocations are resonance stabilized. Carbanions, excuse me. In other words, there's additional resonance forms that you get besides the usual ones that you always get with an enolate. So you get the enolate. The enolate then adds into another molecule of the same. So the electrons in that pi bond remain attached to this carbon, and you'll form a new bond between that carbon and the carbonyl carbon. And you'll push the electrons into the electronegative oxygen atom. So this is the new bond we just formed. We have ethoxy. We have a benzyl group, CH2PH. And we have O minus. And then this is the decision point at which, if we were doing an aldol condensation, we would start to think about dehydration. But remember, this is a Claisen condensation now, not an aldol condensation. There's no possibility of dehydration. And the reason is that we now have a good leaving group on this carbon atom over here. And so the electrons on the alkoxide can just fold back in, reform the carbonyl, and kick out ethoxide as a leaving group. Another thing, again, that could never happen in acidic medium. But in alkaline medium, we're on solid ground. And so what we wind up getting is this beta keto ester. And again, I'm just going to make sure I didn't mess anything up. Yep, that's the same compound. Now, that's the answer to the question. If this were a mechanism question, we would need to take into account this acidic proton, which is not only between two carbonyls, but also benzylic. So it's an especially acidic hydrogen. And so that's going to get pulled off by the sodium ethoxide. And then we would add dilute aqueous acid and put the proton back on. Either way, that's the structure of the compound that you get. Since this question is not asking for the mechanism, we don't need to worry about that. We just recognize we've got our product here. In real life, if we were drawing the mechanism, we'd show the deprotonation by ethoxide ion and then the reprotonation by a hydronium ion. But if I were doing this test, I would just stop right there. That's my product. Good, so much for all of the reactions. We then no doubt have some mechanisms. Let's look at this first one. Looks to me like we're taking this ester, which has two acidic alpha protons, and doing a mixed Claisen condensation. With this other ester that has no alpha protons. So it's very clear the esters on the bottom is going to be the receptor molecule. And the ester on the top is going to be the donor molecule. That's going to be the one that we make the enolate from. I kind of wish that this were the methyl esters so that you don't memorize that it's OET. It might not always be OET. I think it probably is going to be either ethoxy or methoxy. Nearly all esters are either methyl esters or ethyl esters. But the mechanism is going to start with deprotonation at the only place that has any acidic protons, which is next to the carbonyl. Oh, what am I doing? Next to the carbonyl of the top ester. And so we're going to get an enolate over here. That's going to be the first step of the reaction. So there's our enolate. One thing I didn't stress in class, because I don't think it's too important, is we've just generated a double bond, so technically there's stereochemistry here. You could have either the E or the Z double bond. And you, in fact, will get a mixture of both enolates, and it doesn't matter, because that double bond's going to go away and you'll lose the stereochemistry. So if you'd drawn the phenyl group pointing in the other direction, I don't really care. You would get both. And then this enolate is going to add into the carbonyl group of the other ester, the one that's designed to be the receptor molecule. There it is. So we'll put that carbonyl right above. We reform our carbonyl. We form a new bond between this carbon. That's the carbon that the electrons in the pi bond remain attached to, and we'll form a new bond between that carbon and the carbonyl carbon. We've got a phenyl group over here. We've got double bond O over here. This is the bond we just formed. And attached to that carbon, we've got ethoxy. We've got O minus. This goes so much faster with pencil than with ChemDraw. And we've also got a tertial group. So that's the intermediate that you would get. And then the next step of the Claisen condensation has reforming the carbonyl and loss of the alkoxide ion as a leaving group, which gets you, in fact, this very molecule. Oops, I forgot my ethoxy group over here. This is not a ketone, it's an ester. There we go. That doesn't look very nice. Well, the bond angles are nice, but I'm not going to be able to. I kind of have to do that so I don't look like I have another carbon-oxygen bond. And that gets you a structure identical to our product. But as we stressed in class, there's still this acidic proton, and that's going to get deprotonated by ethoxide. You can't prevent it. We're still in alkaline medium. We haven't added the acid yet. So the base is going to do everything it can until there's nothing left that it can do any longer. And so the ethoxide will pull off that proton. And I'm choosing to show formation of the enolate on this top carbonyl. I could just as easily have moved the electrons in between those two carbons and put the minus charge on this oxygen. It's fine. You're just showing a different resonance form of the enolate. You know the rules for intermediates that are resonance stabilized. It doesn't matter which resonance form you use. Any of the valid resonance forms will be accepted. So you now have a double bond over here. And then you get this enolate. And that enolate is going to be swimming around quite happily in the alkaline medium until we add dilute aqueous acid. The first effect of the dilute aqueous acid is going to be to neutralize any leftover sodium ethoxide. And after that's all neutralized, the acid will start to get to work on the enolate. And the enolate will reform the carbonyl. The electrons in the carbon-carbon pi bond will shift out to the hydrogen. Those electrons will remain attached to the alpha carbon. So you're forming a new bond between carbon and hydrogen at that carbon. Then, of course, we break the hydrogen-oxygen bond to form a water molecule, and you get that product molecule back. So that would be what the correct mechanism would look like. You need to show all of that for full credit. Anyone, I guarantee you, who didn't show the deprotonation and reprotonation lost points. We were very clear about that this semester, and I'm generally clear about that every semester that I teach Organic 2. So that's the first mechanism. The second mechanism looks like what we discussed in class just today. We're going from a hemiacetal to an acetal by treating a sugar with an acidic alcohol. We're making a glycoside. In class, I believe we used methanol. This uses acidic ethanol. And I'll also just say right now, you do not have to use all these fancy wedged bonds. Well, I guess you do with the chiral carbon, but the other carbons, okay, I guess they're chiral too. The ring carbons, I don't really care. That would be completely fine. If you want to go to the trouble to draw all those pretty wedged bonds, you can. But the first step is going to be, if you'll recall, protonation of the OH group on the anomeric carbon, on the hemiacetal carbon. This is exactly the same mechanism we discussed in chapter 19. And so in order to put that proton on, we're going to use the acid that we're given, which is the conjugate acid of ethanol, which I'm drawing over there. There's the conjugate of acid of ethanol, so that's going to supply the proton. That will give us this intermediate. And then we can lose a molecule of water, the oxygen that's in the ring. In class, we had a 6-membered ring. This is a 5-membered ring, but the very same thing happens, whether it's a 5-membered ring or a 6-membered ring. At least I think we had a 6-membered ring. We might have had a 5-membered ring, but it would work the same with a 6-membered ring. And so you will get this intermediate. And now when I look at what I'm given, I see that my ethoxy group is pointing down. That means that I need to show the ethanol attacking from below. If the ethoxy group were pointing up in the product, then I'd show the ethanol attacking from above. But since it's on the bottom of the ring in the product, I'll show it attacking from below. And since we're using Haworth projections, we'll use these rather ridiculous bond angles. The intermediate that we get is just like the product, except it's protonated on the oxygen. So that's the intermediate that we get. And again, it looks just like the product. All we need to do is pull that proton off and we're done. And in order to pull that proton off, you use what you're given. And the only alkaline species present is the ethanol. There is nothing else that can act as a base. So the ethanol will pull off that proton, move the electrons back onto the oxygen with the plus charge to get rid of the plus charge, and then we're done. At that point, you have the product. So we did that mechanism today in class. That's formation of a glycoside, in this case, an ethyl glycoside. Looks like we've got a little intramolecular reaction going on in the next one. So we need to figure out where we formed the new bond. And a big key is this carbon over there, which we can see right there. So that carbon is next to this carbonyl. So it looks to me like we formed a bond between this carbon and the carbonyl carbon. So this is an intramolecular aldol reaction. That's where this new double bond came from. So we're going to connect this carbon, which arbitrarily I'm going to call carbon 1. I could just as easily have called that carbon 6 and counted in the opposite direction. Doesn't make any difference. We come to the same conclusion either way, which is that we're going to form a 6-membered ring. We're going to form a bond between this carbon by deprotonating there, forming the enolate and attacking this carbonyl. And again, we've got this landmark of this quaternary carbon. So carbon 1 is going to be over here, carbon 2 over here, carbon 3 with the 2 methyl groups on it. Carbons 4 and 5 are both CH2s. And carbon 6 as the methyl group of the methyl ketone. The oxygen in the ketone gets lost in a molecule of water during the reaction. And we can tell by 2 ways that dehydration has occurred. First, because we're given heat. That shows us that we're going to do an aldol with dehydration. The other way we know that is because we see a double bond in the product. And so this must have gone by an aldol condensation reaction. So it's an aldol reaction with dehydration. The first step is going to be forming the enolate there. The way we know it is to be there is because that's the only set of acidic protons that are going to get us this 6-membered ring with that correct numbering. So in order to know what to use to pull that proton off, we look back at what we're given. We're given sodium hydroxide and water, so we need to use hydroxide ion in order to do that. And I think we pretty much have this down by now. But again, you'll notice with all of these strong bases, I have yet to invoke, I've yet even to write down a sodium ion. Those play no role in the mechanism. They're just spectator ions. Hydroxide pulls off that proton, and we form the enolate. Oops. And again, how did I know to make a 6-membered ring? Because I look at the structure of the product I'm given, and there's a 6-membered ring. So I knew I had to count from 1 to 6 and connect carbons 1 and 6. You just need to pick the 2 carbons that are reacting. And again, the reason I knew to deprotonate here, as opposed to, let's just say, over here, is because if I deprotonated there, I wouldn't get my carbon with the 2 methyls in the right place. The only way we can get that structure is by deprotonating at the one that I've called carbon 1. So there's our enolate. We reform the carbonyl. The enolate then attacks the other carbonyl on the other side of the molecule. And the electrons in that pi bond will remain attached at carbon 1 and form a new bond between carbon 1 and carbon 6. That gets us our 6-membered ring. And so this is the new bond we've just formed. It's the one that's destined to become a double bond in the product. And we're not done yet. I still have O- on that carbon. And so we'll follow the rest of the aldol condensation mechanism through. Next step is going to be protonating that alkoxide ion. We've got to use what we're given. The protic species that we're given is water, so that's what we'll use. Don't memorize that ETOH goes there. It might not be. In this case, it's water. So you get this alcohol, and then at carbon 1, we still have these 2 acidic protons. Since we're given heat, we know that a dehydration is going to occur, also because we see that double bond in the product. So we'll just use hydroxide again as our base. That's going to pull off one of those alpha protons. And we form the enolate. Which will have a double bond right there. So there's our enolate. And then the enolate will collapse, will reform the carbonyl. The double bond will shift over one spot so as to avoid any carbons having 5 bonds. And also to avoid any carbons having 5 bonds, we lose hydroxide as a leaving group, and that gives us the product. And that's basically it. This is an intramolecular aldol condensation reaction that occurs with dehydration. And again, when we lose the water, we get a carbon-carbon double bond that's conjugated to the carbon-oxygen pi bond. That's why the non-dehydrated compounds are pretty hard to isolate in nearly all cases. And they only need just a little bit of coaxing in order to dehydrate, and gentle heating will generally do it. And I'm confident that we would get that compound pretty easily. It's a tri-substituted double bond. It's pretty stable. So that's the mechanism of that one. Then we have just one last mechanism to do. And this looks like we're going to hydrolyze this iminium ion. We talked about that in chapter 23 as well. So the first step of the reaction is going to be water adding to that carbon. You have C double bond N plus, which is going to act like C double bond O. That's going to be a good electrophile. So water is going to add to that carbon. And we went over this mechanism in chapter 23. I don't think we had a cyclic iminium, but it doesn't really matter. The mechanism's the same either way. The only difference is rather than winding up with 2 molecules, we'll wind up with just 1. So the water will attack that carbon and push the electrons onto the nitrogen with a plus charge. And now that nitrogen has its lone pair back. And now, hopefully, by now, we understand that at this point, we're going to have a couple proton transfers. We need to get a proton off the oxygen to get rid of the plus charge, and we need to get a proton onto the nitrogen. So that's going to take 2 steps. The first step is, again, going to use a water molecule. To pull off one of the protons attached to oxygen. That will get rid of the plus charge on oxygen, and we'll go back to a neutral intermediate. We need to do that deprotonation before the protonation of the nitrogen, because if we don't, we'll wind up with an intermediate that has a +2 charge. So first we pull off the proton, and then we add the proton to the nitrogen. The way you know that this can't be done all in one step is because if you tried it, it would have a 4-membered transition state. And the way you know that is by counting atoms. 1, 2, 3, 4. Or you can start at the hydrogen. 1, 2, 3, 4. Either way, you've got a 4-membered transition state. The only reaction we've ever seen that is a 4-membered transition state was the Wittig reaction. And that was an extraordinary case because oxygen phosphorus bonds are so strong. So they're so strong that the system is even willing to form a 4-membered ring. But not in this case. There's nothing extraordinary going on here. So we deprotonate that oxygen, and then we need to protonate the nitrogen using a hydronium ion. I'm still seeing exams where people are drawing hydronium ions wrong. And the structure of H3O plus, I would hope, would be something that we would know by now. There's your hydronium ion. We're using it to protonate that nitrogen. The idea is we're going to lose this entire amino portion as a leaving group. The only difference between this and what we did in class is it's all happening in an intramolecular fashion. Other than that, the mechanism's identical. So you get this intermediate, and then with help from the alcohol oxygen, we break this carbon-nitrogen bond and push the electrons onto the positively charged nitrogen. Let's number some atoms. We'll call the nitrogen atom 1. Atoms 2 through 5 are just CH2s. And then atom 6 is this carbon atom. And that's going to break open the ring and give us a linear compound. And so the carbon, which we formed the carbonyl, is atom 6. And then atom 5 down to 2, those are just CH2s. And atom 1 is the nitrogen. And that nitrogen now is neutral. Got its lone pair back. And so now all we need to do to get our product is just deprotonate that carbonyl oxygen. We'll use a molecule of water in order to do that. And I would again challenge you to look at the version of this we did in class. It's absolutely the same. The only difference is that the amine and the carbonyl compound are separate molecules. In this case, it all happens within the same molecule, but it's exactly the same mechanism. Good. So with that, we're done. That oxygen now has both its lone pairs back. And the nitrogen, of course, also has its lone pair. So that's hydrolysis of an iminium species. We talked about that in chapter 23. And all this looks to be just like what I showed you. Yep. Good. Well, as usual, there's at least one of you who's watching live. Others of you will be watching on YouTube. But you've been very patient. You deserve a cat if I can catch one. So let me see who's available. Ooh, it's dark. No, it's not dark. Here, Molly. Yeah, come here. Yeah, everyone wants to see you. Come here, then. Here's Molly. Has she grown since last time? We'll bring Molly in on that Wednesday of the Wednesday right before final exams start. So far, she's turning out to be, whoops, less scared of people than Barnaby. She's jumped onto my desk. But I don't know that she's really very interested in people, unfortunately. She's more interested in things. She wants to investigate everything. I guess that's typical kitten behavior. Where's Barnaby? Oh, you want nothing to do with being held. You want to investigate. All right, let's see if we can find Barnaby. Barnaby. Oh, here he is. Here, Barnaby. You need to be on camera. Poor Barnaby. He was resting comfortably. But that's my adult cat. He's an old man now. I don't know how old he is, but he's got to be at least 12 years old. So he sleeps a lot, don't you? You don't want to meet any people at all, do you? You only like your human. Okay. So that's pretty much it for this session. Let me stop recording so that hopefully Zoom will finish doing its thing. And if everything goes perfectly, as I said in class today, we'll get this up on YouTube tonight. So thank you all, whoever's watching this. And all of you in my class, I will see you on Monday. Have a good weekend.